Let's solve another thermodynamic problem involving a polytropic process. But this time, let's insert the polytropic process into a series of processes that form a cycle. Carbon dioxide gas in a piston cylinder assembly undergoes three processes in series that begin and end at the same state, and this is the definition of a cycle. Process 1-2 is an expansion from state 1, where P1 is 10 bar and V1 is 1 cubic meter, to state 2, where V2 is 4 cubic meters. During the process, pressure and volume are related by PV to the 1.5 power is equal to a constant. For process 2-3, constant volume heating takes place to state 3, where P3 is 10 bar. And process 3-1 constant pressure is a constant pressure compression process returning us to state 1. Now find the work for each process and the net work done by the cycle. So let's lay out our storyboard. We'll start with a schematic. We have a piston cylinder assembly containing carbon dioxide gas, and we're going to draw a boundary around the gas. So the system that we're defining, the system that we're analyzing, is the carbon dioxide gas. As always, any energy transferred into our system via heat transfer is regarded as positive Q, and any work done by the system on the surroundings, in other words, if this piston were to expand, that's considered positive work. So let's look at the given data. State 1 is completely defined. We know the pressure and volume at state 1. And we also know that the process 1-2, which takes us from state 1 to state 2, is a polytropic process where PV to the 1.5 power is constant. And we don't know the pressure at state 2, but we were given that the volume at state 2 is 4 cubic meters. Now the next process is process 2-3, which is a constant volume process. And that will take us to state 3. Well, if it's constant volume, then we know that V3 is V2. And we were also told that the pressure at state 3 is 10 bar. Now, process 3-1 takes us from state 1 back, or excuse me, takes us from state 3 back to state 1, and it does so at a constant pressure. So let's draw this cycle on a PV diagram. So let's start with state 1. State 1 is given at a pressure of 10 bar and has a volume of 1 cubic meter. And process 1-2 is this polytropic process taking us from state 1 to state 2. And the equation that describes this process is PV to the 1.5 power is a constant. And we also know that state 2 has a volume of 4 cubic meters, but it has an unknown pressure. So I'm just going to label that P2. And then finally, we go from state 2 to state 3, and that is a constant volume process. So from state 2, we're going to go straight up until we get to the pressure given at state 3, which is 10 bar. And finally, the third process in this cycle is a constant pressure process taking us from state 3 back to state 1. So everything is defined for this cycle except the pressure at state 2. Let's write a model that we can use to guide us on our solution. This is a closed system. We'll ignore any changes in kinetic and potential energy as being insignificant. And we do know that the processes form a cycle, which means that it ends where it begins. And we want to find the work done by each of the processes, and we want to find the net work done by the cycle. Well, to begin solving this problem, let's find our unknown pressure at state 2. And we'll do that by looking at the polytropic process equation, where P1 V1 to the 1.5 power is equal to P2 V2 to the 1.5 power. And that comes from the definition of a polytropic process, which is PV to the n power is constant. Now we're looking for P2, so let's rearrange and solve for that. P2 is just P1 times the quantity V1 over V2 taken to the 1.5 power. We can substitute values. We know that P1 is 10 bar, and V1 is 1 cubic meter, and V2 is 4 cubic meters. And we solve for P2 as 1.25 bar. Now let's find the work done in process 1-2. As always, we know that the work is the integral between the first state and the second of P to V. And I've said before, there's no need for us to integrate this again. We've solved this integral in previous problems and have come up with this algebraic expression. We know the work in this process is going to be P2V2 minus P1V1 all over 1 minus n. And this is our solution for this integral when n is not equal to 1. So let's substitute actual values. We have P2 is 1.25 bar, V2 is 4 cubic meters, P1 is 10 bar, V1 is 1 cubic meter, and the value of n is 1.5. And because we have units of bar cubic meters, we'll need to convert that to kilojoules. And solving the math here, we find that the work of process 1-2 is 1,000 kilojoules. That's a positive number, which means that the system has done work on its surroundings, and that's indicative of an expansion process. Let's look at the second process, process 2-3. That was a constant volume process, and so the work integral solution is trivial. dV is 0 in a constant volume process, so the work done by process 2-3 is also 0. Now we need to find the work for the third and final process, process 3-1. And that is a constant pressure process. And the work, as always, is the integral from the first state to the final state of P to V. And previously, we've solved this integral for a constant pressure process, and it's just the pressure times the change in volume. That's the final volume minus the initial volume. Well, the constant pressure during this process is 10 bar, and the final volume is 1 cubic meter. The initial volume is 4 cubic meters. And we have our conversion factor to convert bar cubic meters to kilojoules. And we find that the work done by the system during this process is a minus 3,000 kilojoules. So what that means is we had to put 3,000 kilojoules worth of work into the system in order for this process to take place. And finally, we want to calculate the net work of the cycle. And that's just the sum of the work done by the system during all three of the processes. So it's W12 plus W23 plus W31. Well, we calculated that in the very first process that 1,000 kilojoules of work was done by the system. But in the second process, the constant volume process, there was no work done. And in the third process, the work done was actually negative. So work had to be done on the system. If we add all these together, we get that the net work is a minus 2,000 kilojoules, which is to say, in order for this cycle to take place, we have to provide 2,000 kilojoules to put that amount of energy into the system for the cycle to take place. Now, the work's negative. We're putting work into the system. Even though we got work out on the first process, we had to put more work in on the third one than we got out on the first one. So the net work is going into the system. Also, if you remember the PV diagram, the direction of the cycle was counterclockwise. And that means that this is a refrigeration cycle. So anytime you see a counterclockwise cycle on a PV diagram, you'll know that it's a refrigeration cycle. And that means you can expect to put work into the cycle to get it to take place. You're not going to get work out of the cycle. That would be a power cycle, and a power cycle would rotate clockwise on our PV diagram.